All right, this is from our notes. It's example number 3 and another example of circuit charts like we talked about today in our Zoom. So I'm going to start by looking at my battery and noticing that the positive side of the battery is over here on this side. So that's telling me that the electrons are going this way. So before I start, I need to find the equivalent resistance, but I'm going to talk through the circuit myself so I can try to figure out who's in series and who's in parallel. So if the electrons came out, they would all go through the 2, they'd all go through the 3, so that tells me that those are in series. And then when I get here, I'd have a junction where some of them might choose to go straight and some of them might choose to turn. So that tells me that the ones that turn would be in series, and then the ones that went straight, this line would be in parallel with this line because that's where the choice happened. So that helps me figure out my series and parallel resistors. So I'm going to start by, I think I'm going to combine these guys. I would call this like kind of a mini circuit, something I can combine in the middle of the circuit that will simplify the circuit. All right, remember, we're doing the calculate carry back method, so we need to save some room to calculate up here. So for that reason, I'm going to go down a little bit further, and I'm going to redraw my circuit a little bit smaller. I'm going to put my battery in. I'm going to make sure that I draw it with the positive side on this side. So there's my 12 volts. And we have a 2 ohm resistor. We have a 3 ohm resistor right here. We have a 10 up here. But I am choosing to take the 5 and the 8 who are in series, and I'm going to combine them with an REQ of 13. So I'm going to make sure that I do it in red, and I'm going to make sure that I label it in REQ so I know that. All right, the next step. I think I would combine the 10 and the 13 that look like they are in parallel. So I'm kind of starting as far away from the battery as possible and working towards the battery to collapse them, saving myself some room to calculate here. So I'm going to go down a little bit further. So this then would look something like this. And I'll put my battery back in, so my 12 volts. I have my 2, I have my 3, but now we're going to combine the 10 and the 13. So I'm going to have 1, whoops, let me do parenthesis, 1 divided by 10, parenthesis plus, parenthesis 1 divided by 13, parenthesis 1 divided by the answer, and I get 5.65. So we are going to replace these parallel circuits or resistors with an REQ of 5.65 ohms. All right, so now I have an REQ, a 3, and a 2 that look like they are all in series. So I can do them all in one little step, save myself a little bit of room here. And so I will draw this down here. And I'm going to have my 12 volt battery. And we're going to add up 5.65 plus 5 is going to be 10.65. So we're going to have an REQ of 10.65 down here. 10.65 ohms. Okay, so I have one battery, one resistor. Then I am ready to go on to the next step. The next step is the start of the calculate carry back method. And so I'm going to start by applying Ohm's law. And I'm going to solve for whatever I don't have. So I have a battery of 12. I have an REQ of 10.65. So that tells me that I'm solving for the current. Technically, I'm finding the current that's coming out of the battery. And so 12 divided by 10.65 turns out to be 1.13 amps. All right, so then I'm going to go over and I am going to, before I carry back, I'm going to use P equals IV to find the power that ends up being used up by the whole external circuit if I had everything plugged in together. And so the current times the voltage turns out to be 13.52 watts. Okay, so let's get our circuit chart ready to go. So we have the headings of resistance, current, voltage and power. And we need a row for every resistor. So I have 1, 2, 3, 4, 5. So we need 5 rows here. So there's 1, 2, 3, 4, and 5. Okay. So I'm going to add that extra box down here because remember, everything is now supposed to add up to 13.52 on a good day. All right, let's put in our resistors. It doesn't matter what order you list them. So I'm just going to go kind of top to bottom. I see a 10, a 5, an 8, and a 3, and a 2. All right, so now we are going to do the calculate carry back method and kind of talk to ourselves. And as we learn little tidbits about our circuit, we are going to put them in the chart to kind of help us. All right, so we took our final picture and we calculated, and then we take the answer and we carry it back to the picture before. And this, what we're carrying back is really the current that's coming out of the battery. So I'm going to draw that here. So an arrow, and the current coming out of the battery is 1.13 amps. So let's go with that. Like we now know how fast the electrons are coming out of the battery, 1.13 coulombs per second. So all of that current goes through the 2, and all of that current goes through the 3. We can now write that in our chart. So 1.13 amps goes through the 2 and through the 3. And then 1.13 amps also goes through this REQ. But it's an REQ. So I can't write that in the chart. So instead, I'm going to apply Ohm's law. So I'm going to write down V equals IR, and I'm going to solve for whatever I don't have. So I was just marching with a current of 1.13 amps, and I hit an REQ of 5.65. So it looks like I'm solving for V, for the voltage. And V turns out to be 6.38 volts. So I'm going to take that answer and I'm going to carry it back to whoever made up this REQ. It would have been whatever I circled in my picture over here. All right, so let's talk about this. What does that mean when I carry this back here? So the electrons come out of the battery, they come over here and they hit this junction. And so some of them are going to go this way and some of them are going to go this way. And we learned today or yesterday in our Zoom that in parallel lines, the voltages are the same. So it's going to cost those electrons 6.38 volts to cross this 10 ohm resistor. Like 6.38 sticks of dynamite to cross this mountain here. So I can write that in the chart. To cross the 10, it's going to cost 6.38 volts to do that. It's also going to cost 3.68 volts to cross this REQ of 13. But because it's an REQ of 13, it's not in my chart. So I have to do a calculation instead. So I now am going to go up here and I'm going to write down V equals IR, and I'm going to calculate whatever I don't have. So I was just saying to myself that it was going to take 6.38 volts to cross this resistor of 13. So it looks like I can find the current going through that line also. So 6.38 divided by 13 turns out to be 0.49. And I take that answer and I take it back to whoever made up this REQ. So who made up the REQ is what I'm circling here. And we also learned that within a series line, the current is the same. So that tells me that the electrons that go this way, I'm going to write right here, I equals 0.49. That's what the current is through that line. So current through the 8 and the 5 is 0.49, 0.49, 0.49. All right, so I made it up to my top picture, and I also have 2 things in every row. And once I have 2 things in every row, then I can just do some calculations to finish up my chart. So let's do that real quick. I find it sometimes faster to calculate going across. So to get I, that's going to be V divided by R. So 6.38 divided by 10. So we probably could have done that one in our head. 0.638. But P equals IV, so we're just going to multiply this times. Hold on, my YouTube is playing stuff for me. Don't do that.
Hey everyone, welcome back to my channel. My name is Kristen, and today we are
Kristen. Sorry about that. Okay, so 0.638 times 6.38. That is going to be 4.07. Then I have 0.49 times 5. That is 2.45 times 0.49, 1.20. 0.49 times 8, 3.92 times 0.49, 1.92. 3 times 1.13, 3.39 times 1.13 is 3.83. And then 2 times 1.13, 2.26 times 1.13 is 2.55. All right, the first thing we should do is go back and add these up to make sure that we're good. So I have 2.55 plus 3.83 plus 1.92 plus 1.2 plus 4.07. And we get 13.57. I'll write that off to the side here. 13.57. We're going to call that close enough. Okay, close enough. There's a lot of calculations going on there. Okay, so let's buzz through the questions real quick and see if this makes sense. Let me first start to see if this makes sense. So we learned over here that the equivalent resistance was 10.65 ohms. So we got that. The current flowing from the battery was 1.13 amps. And then I'm going to pause here for a sec. All right, let's go up here. So the current coming out of the battery is 1.13 amps. And so all of that current went through the 2, it went through the 3, so that makes sense. 1.13, 1.13. And then we figured out that some of it is going to turn and some of it's going to go straight. Do we think more of it's going to go straight, or do we think more of it's going to turn? So think of those lazy electrons. If you went straight, you'd have to encounter a 10 ohm resistor. If you turned, you'd have to encounter an 8 and a 5, which is like a 13. They are not going to like that. Okay, so I can predict already that the current going straight has to be bigger than 0.49. And yep, the current going straight was 0.638. And then the 0.49 was the same for both of those. So that kind of makes sense to me. Kind of makes sense. All right, what is the power dissipated by the external circuit? If you plugged in everything at the same time, you would be drawing 13.52 watts. What is the current passing through the 10? That looks like 0.638 amps. The power dissipated by the 3, how much power is used up by the 3? 3.83 watts. The voltage drop across the 2. How many sticks of dynamite to go across the 2? 2.26 volts. At what rate is energy lost? That means like rate that you use energy is like power by the 8. That's 1.92 watts. 1.92 watts. We're going to cross off H. All right, so what if we wanted to measure the current going through the 5? If we wanted to measure the current going through the 5, we're going to use an ammeter. And we know that the current is 0.49 on this entire line. That means that you could put the ammeter here after the 8, between them, or even before the 5. I'm going to choose to put my ammeter right there. And it just means that on this prong, and on the prong of the resistor, I would take the wires and I would hook them together like that. So my ammeter would be sitting in there in series. All right, letter J, if we wanted to measure the voltage drop across the 10. So I'm going to get out my voltmeter. And so here's my voltmeter. And so the voltmeter has those little wires that stick out. We'll put one before the resistor and we'll put one after the resistor. And remember, my electrons are coming this way, so I'm going to have more volts over here. And then when I cross the resistor, I'm going to have less volts over here. And the difference between those, we'll call this VI and VF. If we subtracted them, that's what the digital voltmeter would read out. All right, I'll stop this video and we'll do number 4 on a separate one.